Okay, so last time we tried this F-test for the general linear hypothesis. So we were talking about the cases where you have constraints on beta, and then you would enforce this constraint, and you would get a new model, right? Reduced model. So you had your linear model, and then we would enforce these linear constraints on beta. It would produce under H naught a new model, which would be like, we wrote it as x tilde gamma plus epsilon. So you enforce these constraints that are equivalently written as, let's say beta is v gamma, and then you impose the constraints. If you can write it in this way, there's no restrictions on the new parameters gamma. And if you have q constraints, you would have the size here would be like p plus 1 by q. If you have q independent constraints. And so this really would be x v gamma, which then you call xv. So you plug in v gamma in there. And so you'd get a reduced model in the sense that you have less freedom for the parameters in this so-called reduced model. You can call the original model the full model. And the idea of the test is that you fit both, and then you compare the fitted vectors, the vector fitted values. There was this very interesting, nice geometric picture that we had, that you have, so in this full model, you're projecting onto the image of x, or rather L of x. And then the restricted model or reduced model has the image of x tilde as its model for the mean, or LAX in the book's notation. So this is the image of the reduced model's design matrix. And then you have your, let's say, y vector, which is outside both subspaces. You project it onto the original model, or the full model, you get mu hat. And then you project it onto the reduced model, you get mu hat A. And then you compare the two, so the difference would be, this maybe a little bit too long. So let's say it would be this is mu hat A. And the difference is this mu hat minus mu hat A. So the dimension of this space, I mean, the dimension of everything is kind of known. So this would be mu hat minus mu hat A, and let me specify the other pieces here. So this would be what this vector would be. Anyone remembers? If this is y, this would be E, the residual of the full model. And then you also have the residual vector of the original, sorry, the reduced model, which is this guy, EA. So this mu hat A plus EA would give you Y. And then we can like specify the dimension of these spaces, or the spaces in which these guys live. And these would give you kind of the degrees of freedom of the associated quadratic forms, or the sum of squares that you form. So for example, if you remember, what is the dimension of the image of x, or L of x? Dimension. If you have p plus 1, p covariates plus the intercept. So So basically the dimension of the image of this, anyone remembers? What would be the rank of the matrix, which we assume to be full rank. So the dimension here would be p plus 1. Just you have p plus 1 variables, and the rank is like the rank of X is full, like full column rank. So the space is p plus 1 dimensional. Anyone knows what the dimension of this reduced model would be? Or the image of X tilde, or you can say like the mean model, the dimension of the mean model, or the space that's modeling the mean of the reduced model. Dimension. Any guesses? So you're imposing Q constraints on the bigger the space. So this space is P plus 1 dimensional. You impose Q constraints. Yes. Yes. So it would be P plus 1 minus Q. So you lose Q degrees of freedom. The dimension of this space is that. And then, so let me just remind you. So what is it? So the E lives in, if you remember, lives in this is space, which is LX perp, or image of X perp. So that's where E lives. So what was the dimension of that space? Just a little exercise to see if you remember. You can like specify all the dimensions here. So the dimension of the entire space is n. So these are vectors in Rn. So when you project y is in Rn in general, project y onto the image is p plus 1 dimensional. So if you remove that component, you get E. So you lose p plus 1 dimensions, right? So the dimension of this basically plus the dimension of the L of X would add up to the full space. So this would be n minus p plus 1. So this is where E lives. And so from that, for example, you get this, you divide this by its degrees of freedom to get the kind of chi-squared behavior. Right, or that would be our estimate of the variance. So the dimension of these two add up. So this plus this, the dimension should add up to the full space, which is n. Okay, and then we had another orthogonal complement, which is of interest to us. So this difference of mu hat and mu hat A lives in a space. Anyone remembers kind of a fancier space last time we argued? This lives in a linear space. Zero recollection. There was a fancy symbol that they use. So this lives in Lx minus LAX. So this is the relative orthogonal complement of LAX with respect to LX. So if you imagine restrict our space to LX, that's plane. So this line, the LAX, the green line, has an orthogonal complement which would be in this direction. So together they span the full LX. So that's basically, this is space. This is LX. This is space is LX minus LAX, which is just the intersection of the orthogonal complement of LAX. So it's really LX intersect LAX perp. So you take the orthogonal complement of LAX, but just the piece that's inside the LX. So the intersection is LX. So this is the orthogonal. So this is orthogonal. This line is orthogonal to this green line. Okay, and that's kind of the space in which this difference lives. And so this defines its um, degrees of freedom. So that space together with LAX, so they add up. So because of the way that we wrote it as well. So this, if I add to it this, so it's like LX minus LAX plus LAX, so we get LX. So they add up to LX. So the dimensions add up to the dimension of LX. Because this is P plus 1 minus Q, and this is P plus 1, the dimension of that space would be, sorry, the dimension of this space would be Q. So the dimension of this plus the dimension of LAX would add up to P plus 1. And that's kind of roughly what we did for it's basically the rank of the projection matrix. Remember the projection matrix was H minus HA. So this was a projection matrix. Projects onto that space, and that would give us mu hat minus mu hat A. So this, if you square it, divided by Q, which is the degrees of freedom, which is really the dimension of the space in which it lives. And then you divide by the E. This is E, norm E squared, divided by its degrees of freedom. Again, E lives in the space whose dimension, again, we figure out. So you should be able to figure out all these dimensions by this complementary kind of arguments. And so we divided, and then this is kind of what we last time showed, that this would have an F distribution under null. If you recall. So again, the numerator under null would be essentially this squared divided by Q, and the denominator would be I minus H times epsilon. So these are two different projection operators. Each one individually would be chi squared if I divide also by sigma squared, and they're going to be independent because the projections are kind of orthogonal. And so that was roughly the idea. Anyway, so that's the F test. We have done it in great detail. But this geometric picture is very fruitful if you remember, and there's a lot of things that you can learn from it by arguing about the relative subspaces and also the orthogonality principles. There are a lot of things that are orthogonal to each other, and they form triangles with right angle, and so you can get very interesting geometric intuitions, that we'll get one of them in a few slides. But okay, so that's the F test. So under null has so we wanted to say that if the null is true, this is kind of small. If the null is like violated, they're going to be different. And then you measure how big the difference is relative to the SSE of the full model. And another way of writing this is via this Pythagorean theorem that I believe, also talked about last time. Again, you have this triangle here, right? Mu hat, sorry, this is not mu hat. This is this basically a little bit to like round together. So this EA squared, norm of EA squared, is equal to norm of E squared plus norm of mu hat minus mu hat A, because there's this triangle. So E hat, this is orthogonal. So this E is orthogonal to L of X, which contains the mu hat minus mu hat A. So E is orthogonal to mu hat minus mu hat A. And so they form this triangle with that right angle. So if you write the Pythagorean here, so you get EA squared is equal to norm of E squared plus norm of mu hat minus mu hat A. So we get this Pythagorean theorem. And so norm of EA squared is the SSE, sum of squares of errors of the reduced model. And the norm of E squared is the sum of squares of the errors of the full model. And this is always non-negative. And so the first thing we note is that we can write this as the difference of the two SSE. So alternatively, you can write the F-test as, so this is really the SSE of the full model, and this is the SSE of the reduced model, A, SSE, A, and then the minus SSE of the full model. So this is the alternative form, one in the box here. Alternative form. And the other thing to note is that because this term is always non-negative, we always have the norm of EA squared is bigger than or equal to the norm of EA squared. So what is the interpretation of this inequality? What does this mean? Yes.
You're going to have more error under the reduced model.
Yeah, so the kind of reduced model makes more errors or is unable to explain as well as the original, like the full model, okay? Because you have restrictions on the beta. In other words, the subspace is reduced, so the projection that you're allowed to make has less freedom, so it can't, like it loses some components of y that you otherwise would be able to explain. So this is the case where the null is not true. So you can see there's a component of y in this direction which is lost by projecting onto the smaller model. So mu hat captures it, but mu hat A cannot, and so that's exactly the size of this tells you how much the difference in the errors are. So this is really, again, the different, like, you can think of it as like mu hat A is the part of y which is explained by the reduced model, and so this measures how much it's not explained. So the difference of y and mu hat A is how much it's not explained by the reduced model, and similarly mu hat is the part of y that's explained by the full model, and E measures how much it's not explained. So the inequality is saying that the part that's not explained by the reduced model is always larger, or at least as large as in terms of the size, the norm, compared to the full model. Okay, so the geometric like picture tells you something very natural, intuitive from a statistical perspective. You have like a smaller model, fewer degrees of variation. You have less power to explain your observations. So this extra, the difference kind of, we call it RSS as well, SSE and RSS are kind of interchangeable. Is the difference is the kind of price that we pay by imposing the H naught. Okay. And so today is basically nothing, almost nothing new. So we're just gonna see examples of this, which have specific names, so special cases of this. And once you understand the full picture, it's just these are examples that you can actually work out yourself. But because they're so common, we're going to do it through them. So the first one is like testing for the strength of the overall regression model, or sometimes called ANOVA. And the other is one-way classification, another actually form of ANOVA. But this is what your book calls ANOVA, that we'll see. So here's an example that I think last time I was planning to go over. It's just this case where we discuss is like a set of non-standard constraints. So I just, for example, want to test beta 1 is equal to beta 2 and beta 3 is equal to 0. So if you want to do the test, the F-test, let's say I have 20 synthetic data. I generated 20 synthetic data. I'm not showing the data. I propose the linear model with 3 covariates, right? And 1 intercept. I fit the full model. I get an SSE, which I'll show you later. And then I need to fit the reduced model. That's often the only thing that you need to do to kind of figure out under these constraints, what is the reduced model. And I mean, in this case, it would be simple. We did it. So let's say I call this beta 0, gamma 0, and then beta 3 is 0. So I set it equal to 0. And then beta 1 and beta 2 are equal. So I can call them both gamma 1. And so the model under the null would reduce to y is equal to gamma naught plus gamma 1 times x1 plus x2 plus epsilon. Okay. And so the design matrix for this new regression model is just the columns of all ones. This is like all ones here. And then the column of x1 plus x2. Okay, that's kind of the n by 2 matrix. This 2 is really p plus 1 minus q. Right, p plus 1 is 4. And then we impose 2 constraints, so happens to be the difference is 2 as well. So I fit this model to the data, and what I get is, let's say, SSE is like 4.09. SSE under the restricted model is 43 or something, and the difference is like 39. Looks pretty big, but exactly if I want to measure, is it really a big difference? It feels like it, but the proper way is like to normalize properly. So this F-test allows you to exactly measure it on the proper scale. So I form the F statistic. I get 39 divided by 2 at the top. And the SSE of the full model is 4 divided by 16. And you do the calculation, it's like 76.75, let's say, okay? Is this big for an F statistic? It's pretty big. So you have to compare it with the critical value. In this case would be like under the null, it's the random variable has to be an F with degrees of freedom 2 and 16. So you calculate the upper quantile of this would be 3.623. So we're far above this. And so you would reject. Or you can calculate the p-value would be this very small number. So in the morning session, I did a little calculation. If you don't have a table, if you're a classical statistician, you could do a little calculation to actually convince yourself that this is a large number. I'm going to very briefly mention it, but since we ran out of time, I might assign it as a homework problem. So the point is, so F is like a U divided by D1, U1 divided by D1, and U2 divided by D2, where U is chi-squared with D1 degrees of freedom, U2 is chi-squared with D2 degrees of freedom, and U1 and U2 are independent. So if you don't have access to a computer or a table, you can roughly argue like what is the size of this in case where D2 is large. So when D2 is large, this U2 divided by D2 converges to something. Anyone has a guess of what this converges to as D2 goes to infinity? Yes. That's a good guess, but U2 also grows. So U2 is it's good that you at least had a guess. So U2 is like I from 1 to D2, Zi squared, and Zi's are IID, normal 0, 1. So U2 is the sum of roughly D2, not roughly, exactly D2 Zi squared. Okay, so these also grow. So it's like an average, actually. That's another good guess. Yes, you're very close. So if you continue arguing, maybe you arrive at the correct. So this is going to be 1 over D1, summation I from 1 to D2 Zi squared. The thing is, Zi squared are not between 0 and 1 themselves. Like they're Gaussians, right? Sorry, Zi's are Gaussian. So Zi squared are actually, each one has a particular distribution. What is the distribution of each individual Zi squared? They're chi-squared with 1 degrees of freedom. And then you add up independent chi-squared ones, D2 of them, you get chi-squared D2. So they're chi-squared, so the distribution is really like the tail goes off to infinity, so it can take any, because the normal goes to infinity, they can take large values, but it end like this idea is like there's a limit here in probability, very important, one of the two important results. You take the average of IID random variables, it converges to something. What does it converge to? And what is the name of the law? The name of the limit here. I gave the first word away. It's called law of the first law of thermodynamics. No, it has to be something related. The law of commons. No. What is it? The law of ideal gases. The law of large numbers, right? So, law of large numbers. What is the law of large numbers? This is the most important things, like one of the most important things in probability, okay? What is the law of large numbers? The averages converge to the expectation, okay? So if you have IID sequence of random variables, this would converge to, all of them would have the same expectation. This would converge to the expectation of one of them, which is the I squared, let's say. What is the expectation of the I squared? 1. So this really converges to 1. So your guess was correct. Like it's between, like it's actually 1. Converges to 1. So for very large D squared, the F actually behaves. So as D goes to infinity, really in distribution, or in a more advanced course, you see as D goes to infinity, in distribution, this converges to, you can say in distribution converges to U1 divided by D1. Okay, so it behaves like the numerator only because the denominator just stabilizes at 1. And so it's like a chi-square divided by D1. And what is the expectation of this guy? So expectation as D2 goes to infinity. This happens as D2 goes to infinity. Let me do it a little bit more cleanly here. So F converges in distribution actually to U1 divided by D1 as D2 goes to infinity. And T also behaves similarly. If you go to look at the T also has something. If the degrees of freedom of the T goes to infinity, that denominator goes to 1, so T converges to a normal actually. This F converges to a chi-squared normalized. So what is the expectation of U1 divided by D1? 1. So the expectation of U1 is D1. And then there's the variance, which you can calculate. Variance of U1 divided by D1 would be 1 over D1 squared, variance of U1, which is, I believe, 2D1. So you get 2 divided by D1. So this one you do for like you do it yourself. So what this basically does is allows you a very nice picture. So you'd have a chi-squared, which has like a, when you normalize it, it would be a distribution. It's not no longer chi-squared, but it would be distribution centered at 1. It wouldn't be symmetric. And the variance would be like, would be 1 plus, like if you go 1 standard deviation, it would be like this, 1 minus 2 over D1. So 1 plus minus 2 over D1. So for large values, I mean, so for example here, I mean, if you want to do an approximation, whether 16 is large enough for this asymptotic, this like argument to hold is something debatable, but gives you like a rough idea. So if I assume that this is infinity, basically, then what is it? D1 in this case would be Q would be 2. So I'm looking at something which is D1 is 2. So it would be F2 and 16. So this roughly behaves like U, like a variable which varies in 1 plus minus 1. So 2 divided by D1 would be 1. So if you go 1 standard deviation, it's like 0 to 2. If you go 2, it can't go below 0. So it would be 0 to 3. And so this is really off. It's like 75 degrees, like a standard deviation away. So roughly. So this gives you a way to like reason without worrying about like the tables. It's approximate, but Okay, I don't want to spend too much time on any questions. You can figure it out for yourself, but if you use the law of large numbers, uh, when the second that like d2 goes to infinity, f approaches like a normalized chi-squared. A t-distribution approaches standard normal. And so you can use these to argue because you know things about the normal distribution chi-squared. So anyways, so in R, you can do this by ANOVA command. These are the output of LM commands. You use the LM to fit the two models, and you get the fit and the objects that R gives you, and then you apply the ANOVA, and it gives you all the information about the f-test. It gives you an ANOVA table that we'll see. And then in Python, apparently there is one, which I haven't checked. Okay, so that was an example. And this is the geometric picture again, which we have seen. So today we're going to just work with two like classical examples. These are like the special cases that have like a specific meaning and names of various quantities. They're just special cases. It's just like this, but many more people care about the special cases, so they have different names. So ANOVA would be the case where you set all the covariates equal to 0 except all the betas, the coefficients of all the covariates, except the intercept to 0, because you want to see whether the model has doing anything useful. If you just drop all the covariates, would it matter? And so the design matrix for the reduced model is just reduces to like a matrix with just one column, the column of all ones. And so LAX is just the span of one. It's a one-dimensional subspace. And then we'll see like the mu hat A would be simple, like y bar times 1, and then EA would be the centered response. The other case is the one-way classification in which you have basically equivalently you have a categorical variable with k categories. And you model this as a regression with k coefficients, and the covariates are indicator variables, and you want to check whether these covariates are, or rather the coefficients of these covariates are all the same or not. We'll talk about this. It's like a classical setting. The thing about this picture that I'm going to use briefly is, especially in the ANOVA case, is this angle. So the angle between EA and mu hat minus mu hat A is, you can write some, basically, let's say, if you know a bit of trigonometry, you can write some expression for this cosine of the angle. Right? Can we get an expression? Let me not show you what the expression is. I'll use this briefly later. How do you write the cosine of this? So the angle is between mu hat minus mu hat A and EA. How many people have passed a trigonometry course? High school. Sine, cosine. Anyone? So you look at this triangle. Can you tell me what the cosine would be in terms of these quantities? Yes. Yeah, so the length of mu hat minus mu hat A divided by the length of EA, so the norm, right? Or the cosine squared would be the squared divided by the square. And so you can see these are related to that quantities that appear in the f-test. And so this cosine would like turn out to be like equal, like when you specialize this picture to ANOVA, this side would be r squared. If you have seen in regression, we'll see it later. But it has this nice geometric meaning that we'll see. Okay, so what is ANOVA? You're testing the overall regression, whether it's doing anything at all. Okay, So for that, you set all these coefficients to 0. That would be our null model. And when I do that, again, y is beta 0. Let's say 1 plus beta 1 x1 all the way to beta p xp plus epsilon. Once I set all of these equal to 0, what I'm left with is beta 0 times 1 and then plus epsilon. So that's my reduced model. Right, so my only job is now to fit this reduced model because I kind of know what the full model is. We used to call this gamma 0, so it's okay to call it gamma 0, or I'm going to call it beta hat, or beta 0, let's say A maybe. So we can have beta hat 0A and mu hat A, let's say, and EA. So I want to calculate these. Let's say focus on this one. So how do we calculate mu hat A? The design matrix is really simple here. It's just a matrix with just columns of 1, just a single column. An easy way to calculate this is like via the projection matrix. So apply the projection matrix to y. If you remember, that will give you the fitted value projecting. This one I'll let you figure out yourself. We can first figure this out, then that, but let's work with this. This is the only thing that we need. How do you write down the projection matrix here? Yes.
So A is X transpose X inverse, X transpose.
I'm going to write a tilde, yes. Yes. So, and what would that be? We just see 1 transpose 1 inverse 1 transpose. And does it simplify?
1 transpose 1 over.
Yeah, this is n, so it would be 1 over n. So you get 1 times 1 over n times 1 transpose. We really get that HA is 1 over n 1 transpose. Okay, this is the projection operator onto projection matrix onto a span of 1. Okay, and in general, if you have just a vector, it's good to remember. So projection onto span of v, if v is a vector, if you do the same thing, you would get 1 over norm v squared, in this case, would be like n times v transpose, if you do the formula. Okay, that's good to remember. So that's the projection operator. So once I apply it to my y, what would happen? So what is 1 transpose y? Anyone? So yeah, 1 transpose y would just sum the elements. So if you have y is y1 up to yn, 1 transpose y is just sum of the elements. Right, so this gives me 1 over n. I'm going to pull this out. So you get sum of yi from 1 to n. Because that's a scalar, you can move it around. And then I get the 1. This 1 here is the only vector, actually. Okay, and this is really y bar. Okay, so I get y bar times 1. So the fitted values is just, the vector fitted values is really y bar all the way. Okay, repeated n times. Okay, and then the EA is really I minus HA times y if you want, or really just y minus mu hat A, which is just y minus y bar 1, which is again really y1 minus y bar, y2 minus y bar, yn minus y bar. Okay. So this norm EA squared is really the sum, so I from 1 to n, yi minus y bar. It's the total kind of variation. So it's the quantity that you compute when you want to compute the sample variance. And in fact, if you divide it by, so we know the degrees of freedom of this. How many degrees of freedom does this have as a quadratic form? Yes.
This is the error. As we, I guess it's like n minus 1.
Yes, so exactly. So you enforce one constraint. So you project it. So this guy, basically, if you look at it as like an object, it lives in a one-dimensional space. So whatever is left over lives in the n minus 1 dimension. So the degrees of freedom is n minus 1, exactly. And then so if you, for example, want to divide it by degrees of freedom, you get this, which is really the natural estimate of the variance in that model. This is like our s squared, if you remember, in this reduced model. And this happens to be exactly the sample variance that you see in like earlier courses potentially. And you can get, for example, that this is unbiased for sigma squared. And then if you divide it by, so this is like you can relate it to the chi-squared with 1 degrees of freedom, and n minus 1 degrees of freedom. So this guy, when it will be sigma squared, like the distribution will be sigma squared times chi-squared n minus 1 degrees of freedom. Oh, sorry, yeah, this one, the top, not the divided by n minus 1, but this would be an unbiased estimator. Anyways, so this is what you get. This special case is like, so you get mu hat A is y bar, and then you can also calculate, in this case, I'm calling it gamma hat, but this is really beta hat 0, A, whatever we call this there. So this is the only coefficient, so you're just going to be y bar. And so the geometric picture is that we are projecting onto a span of 1, which is a one-dimensional space. So Lx has p plus 1 dimensions. And so this projection kills, like the hypothesis kills p direct, like p of the degrees of freedom. You only remain with 1 degrees of freedom. Okay, so p is really the difference between 1 and p plus 1. This is our q, which is also clear because you can say the hypothesis like beta 0 equal to 0 and beta 2 is equal to 0 up to beta p equal to 0. So you have p independent constraints. Okay, so once you write down things, this is the E norm of EA, which is that. This is called the SST. I don't know if people have seen this, SST. This is called total sum of squares for an obvious reason. It's just, it's like the variation without any assumptions on y. So you compare the yi to its mean and take the sum of squares. This is really the SSE of the reduced model in this particular special case, but what is called SST in this special case. And so this is really our Pythagorean theorem. If you look at the squared is norm of E squared. Norm of EA squared is norm of E squared. That's the SSE. And this SSR is really this term, the mu hat minus mu hat A, or the additional sum of squares in general. What we call this additional sum of squares. This is, in this particular setting, it's called SSR, sum of squares of regression. Okay, this tells you how well the regression is doing. Okay, so if this is large, so you can see this is basically the total variation is decomposed into the variation explained by the regression, which is this SSR, plus the variation which is unexplained by regression, which is the SSE. Okay, you can think of it as the variation unexplained by the most simple model, which is just the intercept model. Which is just, there's just, that's the minimal amount of it. It's just the total variation, let's say. Okay? The total variation y, which is the variation unexplained by the intercept model, is equal to the variation explained by the regression plus the variation unexplained by the regression. So if SSR is bigger, like big compared to SSE, so they have to add up to SST. So how much of it is picked up by the regression versus left unexplained is like exactly captured in this decomposition. For this reason, it's called ANOVA. It's like an analysis of variance or decomposition of the variance. So you're decomposing the variance of y into two pieces. And in fact, the general formula is a decomposition of variance in a sense. Okay. Does this make sense? It's just we're giving these terms some names, but the meaning kind of is really variability explained by regression SSR versus variability unexplained by regression. And then there are these formulas, some of which we derived, some of which we can derive using the geometric ideas. For example, this can be, you have to argue a little bit. Some terms cancel out because of the orthogonality in the geometric picture. You can do it as an exercise. So one thing that people do often in this special case is write down an ANOVA table, which just summarizes all this information about the t-test, sorry, the f-test into a single table. So we have our the source is either regression, residual, or total, and then you have the SSR, SSE, and SST. So SST has n minus 1 degrees of freedom. The SSE has n minus p minus 1. And the remaining degrees of freedom is p, which is picked up by SSR. This p is really our q here, okay? So this is the equivalent or a special case of that general kind of dimension calculations that we did. And then when you try to form the f-test, you can see it's like the f-test was mu hat minus mu hat a divided by q squared. And then this would be e squared divided by q. Here would be like SSR divided by p. Q is p, and this is going to be, sorry, this denominator is n minus p plus 1. So this would be norm, or that's sorry, SSE. So SSE divided by n minus p minus 1. And so these are, once you divide, you can call them mean squared. Rather than sum of squares, you can call it the mean squared. So the numerator is like SSR divided by p is called mean squared regression, or mean squares of regression, something like that. And this is mean squared of errors, which is like SSE divided by its degrees of freedom. It's like some sort of an average. And then the F is really MSR divided by the MSE in this case, okay? Again, nothing new, it's just some observations and some new notations. And yeah, I think we argued about the ranks and stuff. So that's just how you organize this information usually. You don't have to do it. It's just, you can just write down the f-test, but just good to know. If you do the ANOVA command in R, you get something like this. Okay? Does that make sense? Just maybe you can familiarize yourself. So this is going to have an F distribution with P and n minus P minus 1 degrees of freedom under H, under null, and you can do your hypothesis, and you can either reject or like compare to p-value or whatever you want to do with it. And then the coefficients of determination is really related here to this setup. It's like if you divide this identity that we had, SST divided by SSR, if I divide both sides by SST, I get 1 is equal to SSR divided by SST plus SSE divided by SST. So these quantities would be between 0 and 1. And so one of them is called the R squared. So SSR divided by SST is called the R squared, which is also 1 minus SSE divided by SST. And by that identity, it's going to be always between 0 and 1. And it's close to 1 if the fit is good. So SSR picks up the most of the SST. If it's close to 0, it means that like SSE is basically picks up most of the SSE, the unexplained part. And so it's like a single summary of that kind of variance decomposition identity. It's the fraction of total variability explained by regression, basically. And so if you go back to that geometric picture that I just mentioned, you can see that this is really the cosine squared of the angle that we looked at. And the angle here would be between, this is like the EA. In the reduced model, it's just yi minus y bar. You can call it the centered data. So you look at the vector of the centered y. And this is the same thing, but you look at the fitted values of the regression model minus the centering of y bar. And it's also equivalent, if you understand the projection, it's equivalent to just projecting this. This would be the projection of this onto the regression model. So very interesting exercise to do. But anyway, so this is the angle between these two vectors. And so if this angle is, in the geometric picture, you can see if the angle is like small, the cosine would be close to 1. And so you have a good fit because the y is close to the subspace. If, on the other hand, is like the y is orthogonal to the subspace, then the angle would be 90 degrees, and this would be like cosine of a 90 degrees, it would be 0. Okay, so that angle is really capturing this identity, like the fraction of variability, very nicely. Okay, that's kind of the geometric meaning. If you go back to that picture and specialize, you get this nice geometric view of R squared. So the caveat is this. So if I start adding covariates to the model, what happens is the R squared is going to go up. Because adding new covariates to the model, so far we've been testing like drop all the covariates and see what happens. Now suppose I have the covariates and I start adding more covariates. This you can also compare. Like for example, you can compare if I add 1 or 2 more covariates compared to not. This is another instance of this problem. It's not ANOVA, like typical ANOVA, but you can compare the two models. But adding more covariates always improves, or at least take like, or does not decrease R squared. Yes.
Just adding more variables, I guess.
Covariates, not covariates. Yeah, so predictors or variables. Yes, they're the same thing. So I was saying covariates. Yeah. Covariate or predictor. Yes. Yes, covariate. Not. No, let's call it predictors. Okay, so if I add more predictors, it's less confusing. So R squared goes up. Have you seen this before? So, okay, so it's a problem. So it's not a good measure of, it's a good measure of fit, but it's not a good measure to do model selection. Because if you want to see whether you add more variables, it's better, it's always going to tell you it's better to add more. And what happens is that in the extreme, when you add like n minus 1 variables and you have one intercept, you have now n plus 1 like total coefficients in the model, and you have n observations, and if your rank condition holds, then there's going to be a perfect fit. Okay, so you can explain all the variation. So this would be 1, but that's not good in general. Why that's not good? Yes. It's kind of, you can generalize, yes, but the reason why you can't generalize generally is that the Y has noise in it often. Okay, you imagine if it was noiseless, Y was noiseless, it's fine to perfectly fit. But if you perfectly fit to Y and you know that Y contains noise, you're fitting to noise as well. So that's going to be the problem. So later, the noise changes in new data points. It's not going to be the exact noise that you saw before because it's random. And so that's why you don't generalize. If it was noiseless, it would be okay. But if it's noisy, it's not good to perfectly fit because you also perfectly fit the noise, the exact variations that you know that's going to change later in a new data point. So that's kind of usually the performance, the generalization, if you want. We'll hopefully talk about this at some lecture. Would go down if you like at some point adding more variables. R squared tells you it's good, but if you have a proper like measure of model selection, it would go down, and so there's an optimal way. So one way to fix this, and we'll see in one of the later lectures, a simple way of fixing this is to look at adjusted R squared. So rather than looking at these SSE and SST, you divide by the degrees of freedom, and then you divide them. So like you look at the MSE divided by, you can call it MST if you want. And so this, you can write it in terms of the original R squared. There's this factor here. And so this is more robust in the sense that you're going to penalize. If you can argue for yourself that if you add more variables, this is going to go down. But this is also going to go down, and so it's not obvious that the overall thing is going to go down, right? So this is one of the simplest measures of model selection. We'll talk about this. It's like a crude way of doing it, but there are better ideas as well. But if you do R, for example, they also report this. It's easy to report, and it's better for model selection. Any questions? Okay, one more slide to have some picture. Um, this is trying to tell you what kind of R squared is measuring and what it is not measuring. So the difference between the two plots is that in one, we have a very small beta hat. So this is a simple linear regression. You have intercept and you have beta 1. And so my estimate, I mean, the estimate, let's say, might be close to the truth. You're not showing the truth. But here you can see the slope is very small, relatively. So it's as if it's flat. So it seems like there's not much relation between the covariate and the y. But R squared is very high. Whereas on the other side, beta hat 1 is larger. So you have like a noticeable slope. But R squared is lower. Okay. So R squared is not measuring the so-called effect size, if you want, or magnitude of the coefficient. The magnitude of the coefficient could be very small or could be very large. What it's measuring is this concentration around the line. Okay, so that's kind of the key point. It's measuring the quality of the fit or the quality of explained variation. Here, most of the variation is explained by this line. Here, like a lot of the variation is unexplained. You can see like things are popping up or like up and down. And so R squared is here is small, although this is pretty good. I mean, this is like excellent R squared as far as like some uh, empirical, if you haven't like R squared like this in empirical work, you'd be very happy. This is like nearly perfect R squared. And you have to distinguish the two ideas, okay? It doesn't tell you like there's like, if I vary X, I get a huge change in Y. It may not be the case. Like here, it's like if you vary it here, Y barely moves, but it's a very good um, like model. You have a very good model, except that the relation itself is like, has a very weak kind of, there's a weak dependence between X and Y, but the strength of that relation is high as far as the statistics go. Like you can perfectly explain. There's not much noise. Okay, this is a good picture to have in mind. And here's an example from your book. Let me just go. I mean, there's nothing interesting here. It's just this is an example of a prediction problem. So you're trying to predict gas consumption of cars, and then you have 6 predictors. I don't know if they're engine size or something related to the car. And then instead of the mile per gallon, you try to predict the inverse times 100. Sometimes you modify the observations. This is also like part of the interesting empirical work. You can try to visualize might be easier to predict than the mile per gallon. And so I encourage you to look at the book. I think there's some argument there that we should look at this, or maybe in later chapters. But anyway, so you form this Y, and then you have the data on this Y and on the 6 predictors for 38 cars. And here we want to measure the strength of the linear model that we fit. We want to do this ANOVA business. And so we form this ANOVA table. Here we have degrees of freedom for the SST would be 37 and minus 1. And then I have 6 predictors, so the degrees of freedom of the SSR would be 6. And then the remaining degrees of freedom, they have to add up to the total degrees would be 31. And then you see the numbers. This is like the SSR, this is the SSE, this is the SST, and then you form the MSE, and then the MSR, and then the MSE, and you divide. You get the F, this variable, and you see that you already know that it's pretty big. Here, 37, this is the degrees of freedom of the F that you have to, sorry, 31. So the F distribution with degrees of freedom 6 and 31 is the distribution under the null. And so you look at the, let's say 95 percentile, upper quantile. And that would be 2.41. And so 79 is way above 2.41. So we reject at level 0.05. And then the R and the adjusted R squared are kind of close. But like excellent R squared. So it's like a very good fit. Like R squared is about 94. by 0.94 or expressed in percentage 94%. So 94% of the variance in y is explained by this T predictor, which is very uncommon in real work. Okay, it's a very good model. This sanity check is like, we did a better version of it. Any questions? So this is ANOVA, special case. And there's another one which I want to do, which is a little bit more interesting, so-called one-way classification. Have you seen this before? One-way classification. It's the case where you have k groups, and then each group has a kind of a mean response plus some noise. So imagine you have patients, you divide them into k groups, and then give each one a particular drug. And so Yij is the response of patient J in group I. So I goes from 1 to K, and J goes from 1 to Ni. So you have Ni patients in group I. And so you model the response as some common mean, beta I, for group I, plus the individual fluctuations. These are like individual patients, like vary around the mean. And so one thing that we want to test, for example, is whether beta 1 is equal to beta 2 is equal to beta k. Okay, so if I distribute these drugs, do they have the same effect, or like some of them are different than the others? That's one approach, and this is called like one-way classification. And at first, it may seem like this is not an example, like a special case of the setup that we discussed, because we have one index here, we have two indices. But there's no need to worry, so you can flatten. You stack all these Yij's into a one long vector. Let's say I first, let's say order people, like first I include the group. It doesn't matter if you do it or not, but it would look cleaner when I try to show the design matrix. So you can just stack them in any order you want. But if you do first the group 1, and then the group 2, and then the group K, you get a giant vector, and then the same goes for epsilon, and then there's going to be a design matrix, and then there's going to be a beta, which is going to beta 1 up to beta k prime. Here's transpose, basically. And if you look at the design would look like this. So it would be basically a binary matrix. The first column would be 1 exactly in locations where you have the patient in that group. So let's say the first 3 patients are in group 1. So you have 1 for these rows and then zeros elsewhere. The second column, you would have 1s only for patients in group 2 and so on. Okay. And so these are basically, these covariates would be indicator variables. So they indicate whether you belong to group 1 or not. So if you look at this column, for example, it tells you whether each patient is in group 2 or not. It doesn't tell you about the other groups, right? And you can see this is going to form an orthogonal, like the columns are orthogonal. And this is an example of orthogonal design. And it's really easy to compute the beta hat here. It's going to be X transpose X inverse X transpose Y, and then you can verify, just do it as an exercise. You can verify that if you do this and then unpack, so unpack the result, beta hat I would be just the mean of and the responses in group 1. So in the 2-index model, it would be like Ni, 1 over Ni summation J from 1 to Ni, Yij. So beta hat I would be naturally the mean of this. So it's as if you started from this model on top and just computed the mean within group means, basically. Okay. And the mu hats are also be similar if you go back to the original one. Mu hat Ij would be mu bar. Sorry, Y bar. And so if you look at the errors, Okay, so this is the picture. Maybe I'll skip this picture. So if you look at the error, what is the error? The error in the I should say this would be the SSE basically. The SSE of the full model would be you have to look at this is the mu hat I and this is the yi. So mu hat ij would be y bar I, and so this is like norm EA squared. But once you write it down, it's basically you compare each observation to its mean within the group, and then you sum. So this is a measure of within group variation. Okay, so it tells you, let's say if I plot them like this, so these are the observations of group one. You measure, this is the mean of group one. You measure how far each point is from the mean. Okay, that's kind of the and then you add them up. Okay, so this is, or if you take the average, it would be the average within group variation. For the, there's another one, which is this is going to be there's like a corresponding restricted model. The restricted model in this case would be exactly the intercept model, yes. So this is going to be the full model. When you fit the full model, there's no grand mean up here. So this is going to be the mean within the groups. And so you get, if you look at, this is mu hat ij, if you look at the SSE, it would be this, okay? Why this that appears, this is the SSR. So if you do the SSR in this model, it's equivalent to, I encourage you to do it, it's just the reduced model is exactly the same as, it's a little bit interesting because there's no intercept in this model, but if I impose this constraint, I can say that they're all equal to gamma. So under the null model, there's just one parameter, and then once you write down, it's just going to be the intercept only model in the stacked form. And so mu, like gamma hat would be y bar, just the same thing that we did. And so you would be comparing every observation to the grand mean, and that would be the SSE of the reduced model, and then you can write down what the SSR look like. And the SSR is like, these are within group means, and this would be the grand mean. This is like the mu hat A. So mu hat is just one vector, and then the grand mean, and these are like mu bar 1 times the indicator of G1 up to mu bar K times the indicator of GK. And so when you compare them, you're comparing the within group mean to the grand mean. And so when you write down the SSR, it would look like this. It's just a weighted average of the differences of these group means to the grand mean. So this is the grand mean. So you measure how much these are different. And so this is a measure of between group variation. Okay, so naturally it has this decomposition. You're decomposing the variation into within group variation on average and between group variation. This tells you the total variation in Y. Okay, so it has this very nice geometric, like algebraic meaning, but all of this follows from the machinery that we had. Just specializing to this case as an example, you do it. I just briefly mentioned. And then what happens is, the thing is that you have to be careful here. The number of active constraints or the number of independent constraints are not k, but k minus 1. Okay. Why is that? So you have like, let's say if you have like 3 variables, you write it like this. You get beta 1 is equal to beta 2. You get beta 2 is equal to beta 3. And that's it. It's enough. Once you have this, then beta 1 is also equal to beta 3. So you don't have 3 independent constraints, you have 2. So for k, you'd have k minus 1 independent constraint. So that would be the degrees of freedom of the SSR. SST, the null model would be basically similar. It would be intercept only, so n minus 1. And so the SSE would be n minus k. This is an example where you don't have an intercept separately like in the model. So it's not like n minus k minus 1. So you have to be careful. You just have k variables in the full model, and so you get n minus k. And so then the MSE would be MSE and MSR would be like that, and then you get the F distribution. Sorry, the F is statistic, and it would have this distribution under null. So nothing new except like these SSR again. NSSTs have interesting interpretation as within and between group variation. Okay, once you write things down. Okay, that is. Oh, and then there's this notion thing about the encoding zoo. There are different ways that you can encode. So technically, you have a categorical variable, and here we are doing kind of the cell means. So each like individual, we are modeling individual means as different parameters. But you can take one of them as like you can have an intercept and then measure the differences to that group. Let's say I have let's say group 1 as the reference, and then the mean of group 2 would be that plus a delta, and then the mean of group 3 would be that plus a delta. So this is a different encoding. It would give you the same exact answer in terms of the F-test and things like this, but the design matrix would look different. So this kind of is I won't go through it. I mean, maybe you can have a look and talk to your TA if you want. There are different ways. It's good to know there are different ways that you can impose these or like translate categorical variables to like basically 0, 1 variables, or it gives you different design matrices, but they all define the same subspaces. They all define the same fitted values and residuals, and the resulting F-test would be the same if you test for the equality of the mean. The parameters would be different, like, but that's another point. So here's an example from your book. You have like 4 catalysts, and each one, and you have a bunch of yields, I think, and then each one you did 5 experiments. And so you write down the table, 4 catalysts, you get degrees of freedom 3 here, and then 20 minus 1, and then 16 here. You do it, you get an F-test, which is again large. So you reject the equality of catalysts. Okay, we're almost done. I think one thing that what I will say is maybe the next time I want to talk about this, there is like an interesting thing called ANCOVA, which is if you go to pharma, if you do an interview in a pharma like that does clinical trials, this is one of the things that they would ask. It's nothing like nothing very fancy. It's just in a special case where you have a treatment variable and a baseline, and the baseline is like used as a covariate. So you give a drug to someone, and then you measure before and after. So before would be like the baseline, and this is whether treatment is a binary variable, whether you give them the drug or not. And then the after would be the post like baseline. And then you just regress the post baseline onto the treatment and the base. So this is called ANCOVA, because you see ANOVA, this is called ANCOVA, but then this is analysis of covariance. It's really nothing fancy. It's just because there is a covariance between, I think, the 2 of these variables. And so it's good to know. And then this leads to something called mixed MMRM, which is related to now you measure each patient every, like a bunch of visits. So you give them drug, you measure before, and then every time they come in after in a visit, you measure them, you can write the regression for it. And in this case, the errors within visit would be correlated. So this is a good example to connect to next week, where we talk about the case where some of these assumptions are violated. So for example, if your assumption of equal variances are violated, what would you do? This is an example of that setting. So patients come in, the patient's visits, like once they took the drug, between visits, they're very correlated, the errors. And so we'll talk about it. Just good to know what ANCOVA is. It's not something very fancy. Just put it there because you see ANOVA, there's the C here. This is ANCOVA, kind of. Maybe talk about this, or just good to know. Okay, that's it. Thank you, and then see you next week.